So a fraction can be said as whatever the numerator is per the denominator. So it can be, let's make a new layer here, there we go. So you can have something like 6 per, let's make it more interesting, 19, right? 6 on 19, 6 per 19, 6 19ths, right? Sure. And I've said before that this operation works with anything, not just numbers, right? And if we look at the etymology of this thing, per, what is that? If you look at ancient Egyptian and Coptic, per is house, and it comes into Greek as like a wall. In Spanish, pared is wall. Perimeter is the outside of something. The pericarp is the outside wall of the heart. There's all sorts of things that use per or peri. Person is like somebody from your home. Somebody that has a home, something like that. Paris and Persia are probably also both related to this. Part, the word part, almost certainly. It's like it's a piece of the original thing. Yeah, there's a lot of versions of this. So per, if we look at it as like house, right? 6 is housed within 19. That makes sense. As a fraction, that makes sense. But it also makes sense geometrically with figures, right? So pi on 4. Let's bring this back here. Let's look at this one. So pi on 4, right? Let's get this to move a little bit. There we go. And anchor that. Okay. What does this mean? What does pi on 4 mean? Well, pi represents a circle, and 4 represents a square. And as I've noted before, it's weird that pi is so large. It shouldn't be that large. Pi on 4 is actually the size that it should be. Well, let's look at what happens when we put a circle inside of a square. Like this. So now, literally, the circle is housed within the square, right? So there's 4 sides here. That's the square, right? And the circle is represented by pi. It's enclosed within the square, exactly, right? What is the relationship of the distance around this circle to the distance around the square? If one of these side lengths is 1, the distance around the square is 4, and the distance around the circle will be pi. How about the area? The area of this circle versus the area of this square. If we make the side length of this square 2, the area is 4, and then the area of the circle will be pi. So it's always pi on 4, these two relationships, right? And we can get this, we can get sort of an analogous situation with a triangle, right? So say we're looking at just this bottom half of the triangle, right? So, or it doesn't really matter, but we're just looking at one of them, right? So the area of it is half, right? And then the sides that it takes is half of them. This kind of ends up being this extra thing. But we can get it to be a ratio that uses 4, just like pi on 4 does, right? There you go. Now, well here, so this triangle is 1/2. Now, this triangle here, that same big triangle, is 2/4. But now, each of the fourths relates to one of the sides of the square. So we can bring it back this way, get it to look to talk this same language, right? So 1/2, 2/4. Either way, you have a triangle housed within a square, and for pi on 4, you have a circle housed within a square. Literally, the figure is literally that. So saying this, pi per 4, 6 per 19. That's a very good way to say this, right? And when you say it that way, it makes it very obvious that the top, the numerator, is a number, and the bottom, the denominator, is not a number, and the whole thing together is not a number. The bottom thing is a vector, or it's a unit, so that the whole thing ends up being a vector. You have a number of those, right? A number contained within that. You have pi housed within 4, a circle housed within a square, or a triangle housed within a square. And you can see actually here, right? So there, I split it into 4. This arc right here, the length of this arc is pi on 4 of this. Pi on 4 is the fundamental number, right? If we were to make the perimeter of this square 1, the perimeter of this circle, the circumference of this circle, would be pi on 4. So I'm not taking pi, this magical value of pi, and dividing it by 4. No, the relationship that is represented by the quantity pi on 4 is the fundamental circle constant. And we can get it to manifest with triangles. And you can see that the 1/2 area relationship can be converted into 2/4. Same thing, right? You wouldn't think of the area of this triangle here as 2/4 of the square, but it's valid to. It's totally valid to. So, in the same vein, the area of this circle, you probably don't want to think of it as pi on 4, because why is it pi on 4? What the hell is, why is there a 4 there? Well, there shouldn't be. It's just that historically we've chosen the wrong number to celebrate, and it's 4 times too big. So we have to cut it down by 4 to get it to make sense. But there's still ways to reconcile this, where there is something about the square that is fundamentally there's 4 of. So we can still relate pi and 4 meaningfully. Like, you can still salvage this. It's not the best way, because you could also, because you know, this triangle here, it's obviously symmetrical right here. So if this whole arc is pi on 4 of this distance, it follows that this arc from here to where it touches is also pi on 4 of this, because they're just repeated over here. They're doubled. When you do that mirror imaging, it doesn't really achieve anything, right? And guess how many radians that is between this line and this line, or this line and this line? It's pi on 4 radians. So again, it comes back to you regardless. Pi on 4 is the number. It is the, well, it's not a number. It is the relationship that is fundamental here. Yeah. And division operates geometrically. It operates over everything. It doesn't need to have numbers, and we can speak of it sensically. Right? This is a circle per a square, a circle housed within a square. That is what per means. That is what the division means. Yeah, there you go.